Yeah, the neutrons can only provide a certain amount of degeneracy pressure, which can't hold up against gravity for a certain mass, about 3 solar masses. So there's a limit to the size of these neutron stars. So for very, very massive stars, they can immediately make a black hole if enough mass falls on the core and builds the core up enough. There may be some other object that we don't know about that, neutron stars that are too massive form this other object instead of a black hole. But it seems like we haven't found any other objects like that. Whatever object this might be, light can't escape from it. It seems like it doesn't show up as light. So it seems like there's just neutron stars and black holes. Um, right, and that's we don't know of anything that's stronger than this neutron degeneracy. So we think whatever's left over just crunches all the way down. All the matter goes to an infinitely dense single point, what's called a singularity. Right. So we talked a bit about what happens if you fell into a black hole, and you wouldn't notice a lot at first. Right? All right, if the sun became a black hole, you'd really only notice things at the event horizon, which is, it's the size of a city. So the Earth's orbit really wouldn't be affected. It get cold all of a sudden, but the Earth would keep orbiting. Right? So a light coming from a black hole from outside of the event horizon, but leaving the black hole, would feel a gravitational redshift. It would feel the curvature of space, and it would be shifted as if it were from a source moving away from us. Near the black hole, time would pass slow, and in particular, all right, your volume and your mass would be conserved, but you would feel a different force if you were falling inwards. You'd feel more force closer to the black hole than you would far away. You'd be stretched. And so something like a 3 solar mass black hole, the tidal forces would kill you. Right? So assuming you could survive that, then you can discuss what you can see. But otherwise, the tidal forces near a small black hole would spaghettify you. Now, near a supermassive black hole, it's not as bad because the event horizon is farther out. The tidal forces as uh, aren't as big. So this is the thing: we can't see black holes in principle. So we can ask, do they really exist? And we have some evidence for it. Right? We've talked about some of the evidence already. Right? So to know the properties of it, you need to be able to measure orbital properties of some companion or measure the properties of gas that's orbiting it. And you need to be able to find a thing where you can't see it, but you see all the stuff around it orbiting. And we see there are some binary systems where we see an object orbiting, we see it in X rays, and we see the accretion disk essentially. We don't see the object it's orbiting. And it seems like it's a black hole. One example is so if you remember the Star Tours, um, beside the Big Dipper, there was what's a cross shaped, was it supposed to be a swan? It's called Cygnus. And I'll go back a second. There it is. And in the body, there's a little star that is basically a binary system you can see um, in X-rays, and there seems to be an object there that. All right, so this was the first detection. First time we were like, we're pretty sure that's a black hole. All right. So there's a few others, right? Gravitational waves imply that we're seeing black holes collide, and there was the attempt. You can look this up. The attempt to image a black hole, and they basically saw the accretion disk and saw the hole clearly around it. And so there's a few different attempts to find these black holes, and we're pretty sure they're there.